Alright, let's start today's lecture with a quick recap of an electrochemical cell and try to clear up some of the more confusing concepts that we've seen before. So first off, let's recall that an electrochemical cell is split into two halves that we call half cells, and on each side, half of the overall redox reaction will occur, and so we represent redox reactions as half reactions. We know one side will be reduced and the other will be oxidized. But we write out our half reactions from the reduction point of view, and then we judge based on their reduction voltages, or potentials, which is the one that will actually proceed as written, and which one will go in reverse, thus releasing electrons to be gained on the other side. And whichever reaction has the more positive potential is the one that will proceed in the forward direction. And more positive is the key term. Fuck you, PowerPoint! Just fuck you. And more positive is the key term. After all, these are both negative numbers, but this voltage here is more positive than that one. And so lead 2 plus will gain the 2 electrons, which means that tin is going to lose the electrons. And so electrons will travel from the tin side to the lead side, from anode to cathode. And we will harness the energy associated with that electron transfer. And the energy that we can get from each electron is going to be based on the overall voltage or electrochemical potential of the cell. Now, what can be very confusing about the setup is where are the cathode and anode going to be? Like, what parts of this are set in stone and what parts are flexible? So here's what's set in stone. The positive terminal on the voltmeter, or positive wire, is always on the right side by convention, the negative terminal is on the left. The line diagram of the cell is always going to be negative terminal on the left side, salt bridge, positive terminal on the right. What else is set in stone? The cathode is always the one that has the more positive reduction potential. Finally, the electrons will always flow from anode to cathode, because by definition, anode is where electrons are lost, oxidation occurs, and cathode is where they are gained, reduction occurs. Here's what's not set in stone. The terminals that the cathode and anode are hooked up to. To draw some parallels with the real world, calculator and battery. Here in the calculator we have the terminals, which we know have this plus sign and negatives. And so that's analogous to those terminals on the voltmeter, right? And so this spring here is always the negative terminal, and it doesn't matter how I hold the calculator. The negative terminal is always there. Battery, this part jutting out up top has a plus sign. This is the positive electrode. This is our electrochemical cell. And on the bottom, the negative electrode. And it doesn't matter how I hold it. This is always the positive electrode, this part jutting out. The part that I have control over is how do I put the battery into the terminals of the calculator. Do I align them properly? Or do I flip it upside down, right? Of course, if we flip it upside down, the thing won't work. For a voltmeter, the consequence is that the voltage that it would read would be reverse of what the spontaneous reaction actually is. And so let's talk about that potential, both from the reaction and from the voltmeter perspective. So from the reaction's point of view, the overall voltage is simply the reduction voltage of the cathode plus the oxidation voltage at the anode. And so the reduction voltage of the cathode in this particular example is negative 0.126, which by itself looks rather unfavorable. It's negative, and we want voltages to be positive. But because this one is going to flip and be oxidized, its voltage becomes positive 0.136. In other words, it's just the negative of its reduction potential. And so when I add the two numbers together, I do get an overall positive and thus favorable voltage of 0.010. And so that means that the cell releases 0.010 joules of energy for every coulomb of charge that's transferred from anode to cathode. That corresponds to about 6 times 10 to the 18th electrons having to move from here to here. Now what the voltmeter is going to read is just the voltage difference between anode and cathode from the reduction point of view. And the voltmeter doesn't care what's hooked up to each side of it. It's just going to take the reduction potential of this electrode on the positive wire, in this case tin, and it's going to subtract the reduction potential of what's hooked up to the negative wire. And so we just have minus 0.136 minus 0.126. And when all is said and done, we get the same number as over here, but it's negative. Because this cell is hooked up backwards from what we would usually expect, where the more positive potential cathode should be hooked up to the positive terminal. If that was the case, these numbers would be identical. Now, so far we have kept things simple and always done everything in 1 molar aqueous solutions, thus keeping everything at standard state conditions, where we can use these voltages here. But what happens when we're not at 1 molar? Well, then we need to use something called the Nernst equation to figure out the proper voltage. So let's make some notes. All right, so Nernst equation, N-E-R-N-S-T-E-Q. And let's just write some generic reduction half reaction where we have some chemical A plus electron yields some other chemical B. And for coefficients, let's use lowercase letters for the chemicals themselves. And for the electron, we will use N to represent its coefficient. And to complete this, we recognize that the reaction could go backwards as well and form an equilibrium. What the Nernst equation is a way to calculate the actual voltage of this reaction if we're not at standard state by starting with the standard state voltage and applying a modifier to it. And that modifier consists of quite a few parts. So let's just write it all down and then make sense of it. Capital R T over N F. Natural log, and then a ratio of our product concentration, in this case there's only one product, B, to the reactant concentration. In this case, we only have A, and then we raise those concentrations to whatever their coefficient may be. So, looking from left to right, here we have 3 constants. R is a constant which you could look up, you learned about it in Gen Chem. Temperature, we will assume, will be a constant value in this class, and will typically just default to 25 degrees Celsius or 298 Kelvin. And then F is the Faraday's constant, which we learned in a previous lecture. So we can combine all 3 of these numbers into one constant, which is 0.05916. We'll write that down momentarily. N is not a constant because we don't know how many electrons are going to be transferred in a redox reaction. And then this right here should look rather familiar. Products over reactants. What is that like? And you should think that it looks like an equilibrium constant. And it's the exact same expression, except instead of calling it K, we're going to call it Q, because this represents the ratio of product to reactant at any time, whereas K just represents that ratio specifically at equilibrium. And this is where our concentrations have a major effect on what the true voltage winds up being. So let's just write down some simplifications and then understand this a little bit better. Alright, so here's how we're going to simplify everything up to the natural log. R times T over F is going to be equal to 0.05916. This is provided that our temperature is at 25 degrees Celsius. So at 25 degrees Celsius, that's what those constants will group to. Again, we don't fold in N. We keep that separate because some reactions might involve 1 electron transferred, another might be 2 or 3 or maybe even 4. Now, that 0.05916 actually combines one more number in addition to the R, T, and F, and that would be the number we need to convert from natural log to just log, or log base 10. And you'll prove this on the homework, so you'll get to see firsthand how it all winds up working out. So we have that log, and then this is Q. And we'll make the note that Q is just the same as the K expression, but it's at any time, not just at equilibrium. And so Q is where our concentration effects on voltage come into play. If we were not at standard state, we would have to plug in the concentrations into here, then solve for the log, multiply by this, and then whatever we get as a result is subtracted from our standard state voltage, which we would look up, and then we learn the true voltage of the cell under those concentrations. Now, we'll see later that the Nernst equation is extremely important for analytical chemistry. After all, one of our major questions is how much of something do we have? Now we have this equation that relates a measurement like voltage to a concentration, i.e. what we're analyzing. But how is this interesting in just the normal real world? Well, how many times has this happened to you?
Alright, you got the directions plugged in?
Yeah, but there's less than 10% battery life left, so I'm a little nervous.
If only I had a charger we could run that battery like an electrolytic cell and promote the non-spontaneous redox reactions. Well, hopefully it lasts. Alright, light just turned. What's the next direction?
I don't know, I'm freaking out. It seems like the battery's dying faster than ever.
Get a grip. It's all in your head.
Not necessarily. Let's see why. Don't write this next part down, just follow along with the logic. Recall that our device needs a certain power to operate, a certain amount of energy per second. And that power is equal to the current of the cell times the voltage of the cell. And now I'm going to make a rough plot of voltage versus battery use. And so at the very beginning of the battery's life, we have maximum voltage. But once the battery begins to be used and the reactions start to go, here's what will happen. Reactant concentrations will go down, product concentrations will go up. Both of those effects will cause Q to grow larger, which causes this entire term to grow larger. But this whole term is ultimately subtracted from another value. We can see there's that relationship here. So the voltage is going to keep going down more and more as reactants go down and products are made. And so the voltage begins to decrease with use. But it doesn't decrease in a linear manner because we have that log term. And the way that log term is going to affect this graph is like this. And so here's the vicious cycle that happens. You start using your battery, the voltage goes down. But your app requires the same amount of power. So the only thing it can do is draw a faster current from the battery. Well, that causes your reaction to proceed faster. So now your reactants are decreasing at a fast rate, your products are increasing at a fast rate, that Q is going up, your voltage is going to decrease at an even faster rate than before. And so now the battery will start to run even faster than before. And we get this vicious cycle that speeds up until kerplunk. And that's why your battery seems to die faster when you get towards the end of its life.